So, hello everyone. So, we are going to discuss the next lecture of this module, that is drying. So, we will quickly revisit the last lecture. So, there we discuss on membrane filtration, particularly the separation based on the size. So, there the driving force is pressure difference or pressure drop, you can say, and resistance comes from the membrane itself. Then resistance comes from the concentration polarization, plus resistance comes from the membrane fouling. So, we discuss the theory of membrane filtration, where you can apply the Fick's law to relate the inlet flux and outlet flux to calculate the rate of membrane filtration. In addition, we also discuss the flux can be related with mass transfer coefficient or the film theory. So, further we discuss different membrane filtration equipment. So, basically it will have different setup, it should be compact and it should have the filter units, and there were different type of filter unit like hollow fiber and so on. And further, depending on the size of the pore, one can call it is a microfiltration, nanofiltration, ultrafiltration or reverse osmosis. And depending on the size cutoff, particularly in the bioprocess, we apply the microfiltration and nanofiltration or ultrafiltration for some cases. But the reverse osmosis is mostly used in the water purification, not in the bioprocessing. So, in today's lecture we will be focusing on the drying. So, we will first discuss what is moisture content or humidity and how it is taken care by or how it is removed by the drying. So, we will see what is the drying kinetics and mechanism, how it works, then how you can find what is the drying time, then what are different modes of drying, it can be batch and continuous mode. Then we will quickly see what are the different type of drying equipments. So, drying, as the name suggests, it is removal of a small amount of water, or you can say residual water or moisture content. It may also be some organic liquids from the solids, from the process material, from your product. And this moisture content in the final dried product varies depending on the type of product. So, what is the desired moisture content, and accordingly you go for the drying. For example, if it is dried salt, it has 0.5% water, it is coal 4% water, food product it can have 5% water. So, typically it ranges between 0 to 20% or so. So, in general this drying is the final processing step before packaging of your desired product. So, why we need to do drying? Because you may making the product suitable for packaging and storage, and once moisture is not there, so it prevents the degradation, particularly oxidation or aggregation of product during the storage. And typical drying process involves passing of hot air that supplies the enough heat for the vaporization of the moisture. What is the limitation? It has a certain limitation, because if there is a biological macromolecule or biological product which is heat sensitive, so for that drying cannot be used. In that case, there are different variations. Apart from atmospheric drying, one can go for vacuum drying or the freeze drying, which is suitable for heat sensitive macromolecules like proteins. But in all the cases it require the energy supply, and if it require the energy supply, means it is an energy intensive unit operation, and there are different factors like dryer effectiveness and energy efficiency. These two decides are particularly governs the economics of whole drying process. Now, how you define what is the water content or what is the humidity. So, when we say it is a humid or when we say it is a moist air, it means it has dry air plus it has some water vapor. The same concept comes if I say humidity of air, or you can say absolute humidity or humidity ratio. It is defined as the mass of water vapor mW, mass of water vapor carried by the mass of dry air. So, you can say it is a absolute humidity or humidity ratio, and typically you use this hygrometer to measure the humidity. So, many times it is not possible to measure the weight. So, it is possible to measure the partial pressure of water vapor, and as you know this partial pressure of water vapor is proportional to the mole fraction into total pressure. Now, this total pressure will be sum of partial pressure of all its constituents including water vapor. So, now this same humidity can be written in terms of partial pressure of water vapor in the air to the saturation vapor pressure of the pure water at the same temperature, and this term is called the relative humidity. So, when you are relating the ratio of partial pressure of water vapor in the air divided by the saturation vapor pressure of the pure water at the same temperature, that is called the relative humidity. Now, again the maximum humidity happens at a particular pressure and temperature. So, it causes air to be saturated with its water vapor, and at this condition this partial pressure of water vapor in the air is equal to the saturation pressure of water vapor at that given temperature. And in fact, when we say this dew point or saturation temperature, this is the temperature at which the mixture becomes saturated. So, it means when it will be saturated, because the partial pressure of water vapor in the air now it is equal to the saturation vapor pressure of the pure water at the given temperature. So, that is why you can say it is dew point as a saturation temperature. Now, if you want to understand the drying, the crude way you can think of that the rate of drying is proportional to the decrease in the moisture content dx upon dt, and also it says this is proportional to the what is the mass of completely dried solid. So, it says now n becomes minus ms into dx upon dt. Further, you can define this based on the drying per unit area. So, in that case you can write a small n, then it will be ms upon a dx upon dt. And when you want to calculate the drying rate per unit mass of dry solid, so ms will not be there. So, you can directly write n m equals to minus dx upon dt. So, what is important here is to know what should be the area required for the drying. So, drying here the both, as we have seen, the heat transfer, because the temperature is required for the evaporation of water, as well mass transfer is taking place simultaneously, and it may also lead to change in the physical property of the solid. So, that is what we told, that we need to be careful with the heat sensitive materials. It removes water by the means of vaporization and using the heat supplied. And how mass transfer is taking place? Water within the solid is evaporated to outer surface either as liquid or the vapor. So, water is going out from the solid in form of water vapor, and you can see the typical drying curve. So, you can think in terms of drying time as well as the water content. So, you start with the A. So, when we initially start, the first is called the heating of period. So, this A dash, you can say it is a heating of period. It reaches to the temperature of the hot fluid or hot gas, whatever you are passing through it. Then it comes to this A dash to B, that is the constant rate of heating. Constant rate of heating means the surface water is being removed and same amount of water is again coming at the surface. It means the water removal or evaporation is at the equilibrium. So, rate is a constant. Now, once the surface water, there is no sufficient rate of water coming at the surface as it is being removed, or you can say the rate of drying exceeds. In that case, you will see the first falling period. In that case, all the surface water will be removed and you will see some formation of dry patches. Now, once it is done, then further you will just see the second falling period. So, here the internal moisture, whatever internal moistures are there, that will try to come out through the diffusion. So, you may see the formation of crack or some surface deformation may be there, because this is the surface water and second falling period, you can say this is a kind of internal moisture, you can say. Now, reverse of this drying rate curve, it comes when you replace drying time with the humidity or water content. So, water content was highest at the starting and it decreases for different phases of the drying. So, you just say there is slight decrease here and during the constant rate the humidity or the drying rate is constant from A to B. Now, further B to C is here constant rate. Now, C to D is the first falling rate here. So, you just see here again there is a decrease in the drying rate, and considerably one can read what is the value of water content. And finally, if you just see it when it goes further down, this is the corresponding to the second falling rate, and finally it reaches to saturation at certain humidity or water content that we call as the critical moisture content. It means beyond this point further moisture cannot be removed by the drying. Other option may be then you can go for the burning of the material. So, there is a critical moisture content here beyond which the moisture content removal is not possible. So, drying curve, now you can understand that it shows the rate of drying changes with respect to moisture content in the solid. So, first you have this induction or warming up period. So, in that case solid loses water quickly. So, you can see this there is a sharp decrease, but for very small amount, and surface stay wet and drying rate is constant, and then external factors like air or environment control this phase. Now, when we go to the falling rate period, so as drying continues, critical moisture level reaches and the rate of drying goes down, and this is controlled by the internal factors like heat and mass transfer within the solid, and in this case slowly evaporation slows down and it reaches to the plateau. Further, if there is a hindered or diffusion controlled drying, so here drying is limited by the property of solid and water is transported from interior through the diffusion process. So, you can say this process corresponds to the second falling period, second falling rate. Now, it reaches to final moisture content x naught, no further decrease in the moisture level. So, this corresponds to the. Now, what are the factors which are going to affect the drying rate? What is the shape, what is the thickness, and what changes happening inside the material. In practice, the real material may not follow the ideal drying curve, there may be some deviation, because material may shrink, there may be crack formation, it may harden or it may change its structure. So, this make drying curve more complex depending on the nature of material, and sometime there may be hard crust forms over the surface that traps water and slows down the further drying. So, it says that upper layer has been dried up and but still the moisture content is there in the internal part. Now, we already seen the what is the equation of the rate of drying. It says NC minus MS dx upon dt. So, if we integrate this, so it should be 0 to let us say T1 is the drying time, dt is equals integration MS upon NC of dx upon dt. It goes from x naught to x1. So, this will be delta T equals MS upon NC x naught minus x1. So, in this way this is very simple. If you know the initial and final moisture content and then you know the rate of drying, then you can calculate the drying time. So, it says the drying time required to achieve the desired state of dryness. Now, what are the different drying methods? So, we can operate in both batch as well as in the continuous mode. In the case of batch mode, the material is kept inside the drying equipment and drying is proceeds for a given time. Let us say you put in the oven for 30 minutes, for 1 hour or even for the overnight, that is a batch drying, and as the time ends you have to come out and take the sample. In the continuous drying, the material is continuously added to the dryer and dried material is continuously removed. So, it works in the both batch as well as in the continuous mode, and depending on the physical condition you can say it is atmospheric pressure drying or vacuum drying or the freeze drying. The atmospheric pressure we have discussed. Now, what is the vacuum drying? In that case, this tray and let us say enclosed rotary dryer, it operates under vacuum or the you can say the indirect heating. Now, typically what happens, this water boiling point, if you increase the pressure, the boiling point increases, and if you decrease the pressure, the boiling point again decreases. So, under vacuum it evaporates even at a lower temperature. So, evaporation of water takes place at lower temperature because we are lowering down the pressure, and this is suitable for the heat sensitive fermentation product. And alternative of vacuum drying can be the flash or spray drying. So, in the case of spray drying, this is a rapid drying process and drying time is very less, you can say in few seconds actually. So, it says the rate of drying under vacuum is greater than the rate of drying at atmospheric pressure. So, there is advantage for this process because the thermal damage from the prolonged exposure of heat can be avoided. Further, there is disadvantage because there may be formation of dust particles which affects the biological activity. Now, in the case of freeze drying, there is slight change in the principle of evaporation. Earlier we said the removal is by evaporation, now here the removal is through the sublimation. Sublimation means water is directly converted to the vapor without going to the liquid phase. So, for dry unstable or heat sensitive product at low temperature, usually less than 0 degree centigrade, it maintains the chemical composition and prevents against any heat damage. So, how it works? You freeze the product exposed to the low pressure and there the sublimation of frozen water takes place. The sublimation, it leaves the networks of cavity within the solids and makes high internal surface area, but it has a disadvantage because it is a energy intensive drying process, you need to now you require energy for the cooling, and here the drying time depends on material thickness. So, if it is thick material, it takes a long time for the freeze drying, and here the typical freeze drying cycle is about 24 to 48 hours, and applications, particularly if you are dealing with pharmaceutical products like protein, vaccines, vitamins, antibodies. So, for those cases the freeze drying, and even in the laboratory practices, particularly for the research applications, the freeze drying is quite frequently used. Now, drying equipment. So, most dryer operates at or close to the atmospheric pressure. So, there can be two modes of drying. One is direct mode of heating, in that case air entering the dryer gets in contact with the wet solid and further drying process takes place. In the case of indirect mode of heating, you apply the indirect heat to dry material through, let us say, metal wall or the tray. So, depending on these two modes, there are different set of equipment which are available in the for the drying purpose. So, you can, I have listed a few like the tray dryer, vacuum self indirect dryer, continuous tunnel dryer, rotary dryer, drum dryer and the spray dryer. So, now these are the different configuration of those drying equipment. For example, if you just see, this is a tray dryer. So, what you have to do here, there are different tray. In that tray you have to keep your sample or your product which you want to dry in the tray. Now, what you are doing is the air will be coming here, and then this will go out here, and through this way the air will be recirculated among the tray and through the tray, and if the surface is if the surface is exposed, and through the surface this evaporation or drying will take place. So, in that case this tray dryer you can operate in a batch mode, because once you have loaded the material you have to wait for drying cycle to complete, then you can take out your material. You have to clean the tray, then next batch will be ready. But if you look at the spray dryer, so what you are doing, you are feeding liquid feed, and typically it works under vacuum. So, what you are, this is the spray chamber and you are spraying, and by the time it, of course, you are passing the heated air to maintain the temperature, and by the time it reaches down, this liquid feed is converted into solids, typically in the form of powder. This is the droplet and it is converted to the powder, and then it will come out here, and there you are getting a dried product. In addition, that if this powder is may come out with the air also, for that you need to have a cyclone separator, that from the air you have to separate the part of your product, because it will minimize the loss of your product. So, from the air stream you need to use the cyclone separator and hopper to get your product back. So, most of the product will come in this route, but from the cyclone also some of the product which was going through the exhaust gas or air, that need to be recovered. So, in this way this those dryers can operate in a batch mode, or like a spray dryer you can operate in even a continuous mode. And these are different configuration: tray dryer, vacuum self indirect dryer, continuous tunnel dryer, rotary dryer, drum dryer and the spray dryer. Now, we can quickly see the application of drying in, particularly in bioprocessing. So, for drying of enzymes, protein and pharmaceuticals. for preparation of products like where say desired level of moisture content is required, the probiotics or even microbial cultures. Then stabilization of vacuum and biologics, because there is certain regulatory requirement as well as in terms of what should be the humidity or the moisture content, and the production of powdered food additive and nutraceutical. So, particularly in the nutraceutical, you just see there are many protein samples are there, milk powders are available. So, those are the product of a drying process. Now, what are the advantage and disadvantage of drying as compared to the other processes? So, as we know, if you remove or control the moisture, we can enhance the stability as well as the shelf life. And once you are removing the, as I told, total mass will be F will be this, let us say X is the moisture content plus S is the solid. So, once you remove the X, so there is a reduction in the weight and volume, which helps in easy transportation, and in addition it enables the formulation of powders and granules in a better and efficient way. But there are certain limitations, as I told, this drying is a heat sensitive process. So, the material need to expose to a certain temperature to remove the moisture content. So, there may be potential loss of activity if it is energy sensitive product, let us say protein or enzymes, and it require the input of energy, and further this you need to have a sophisticated instrumentation and operational cost, particularly if you are going for this vacuum drying or freeze drying, because there you need sophisticated vacuum device, then controlled temperature device. In addition, there you require very good quality controller also to control the desired temperature and pressure. So, with this I will stop here. So, today we discuss the drying. Particularly drying means you are removing the moisture content or humidity, you want to maintain a certain degree of humidity. How do we define the humidity? It is a relative term, and the relative term of mass of water divided by mass of dried material, that can also be represented in terms of partial pressure of water divided by the saturation pressure, and that term is known as the relative humidity. Then we discuss the very simple, the rate of drying. We are considering the whole mass is getting evaporated, and rate is proportional to that minus dx upon dt. And if you integrate it, you can also calculate the what is the drying time requirement. Then drying operation you can operate in both batch and continuous mode, and there are different configuration of the equipments. We discussed two of them, spray dryer and the tray dryer. Thank you so much.